Okay, so today we delve into a much more complex problem involving a system of pulleys. Okay, so this is a problem that has been published by a well-known Russian author and physicist Irodov, and the solution for this is found in various locations. So the reason I chose this problem was to illustrate how to choose a frame of reference and make that a, a way of solving this problem much more easily. Right? So we want to solve this problem in a much more elegant manner by appealing to our intuition. Right? Uh, so here, so there are several assumptions that are there, and one of the assumptions is that this mass here is sliding on a surface with no friction. The the strings here have no mass. These pulleys are also massless, and they are free to move. Okay, so we are not constraining the motion of these pulleys in any way. So under these circumstances, we want to find the acceleration of m1. So now if we see here, the, the tension in this segment is equal to the tension here. The tension in this segment is equal to the tension there. And why is that? Because these strings are taut. Okay, these strings are taut. And so the consequence of that is that the acceleration of m3 is equal to the acceleration of the pulley 2. Right? Pulley 1 doesn't move here. So the acceleration of m3 would be different from that of pulley 2 if the this pulley had a mass, or it was not so easy to move it. It had some frictional force that prevented its free rotation. Okay, so which we don't have that. So uh, let's try to see how to solve this problem. So here the T1 is the tension of the string that's pulling M3. So this is the Newton's law for of motion for M3, that is T1 equals M3 times A3, where A3 is the acceleration of mass M3. Now if you look at pulley 2, so and we construct a free body diagram. So the pulley 2 is being pulled upwards by tension T1, right? And then it's being pulled down by tension T here and a tension T there. And why is that? Because M1 is being pulled upwards by tension T and M2 is being pulled upwards by tension T. So the forces on the pulley are equal and opposite. Okay. So here, if you look at the free body diagram for pulley 2, there's T1 going upwards and T going downwards. So T1 equals T plus T equals 2T for pulley 2, right? So now is where we have a sleight of hand and we fix a reference frame on pulley 2. So here we find the relative acceleration of mass m1 with respect to pulley 2 and relative acceleration of m2 with respect to pulley 2. And the relative accelerations are the same, but they are opposite in sign because m1 being greater than m2 is moving downwards and m2 is moving upwards. Right. So if you look at the free body diagram for m1, T acts upwards, m1g acts downwards. So the net force is m1g minus T equals m1a. So if you look at the free body diagram for m2, the weight of m2 acts downwards, tension acts upwards. So the net upwards force is T minus m2g, okay, and that equals m2a. Now, we know that the accelerations of these two are relative accelerations of these with respect to the pulley are equal and opposite in sign. Now, the thing with the real acceleration, that is with respect to a reference frame that's fixed on the ground, okay, so is nothing but the acceleration of m1 with respect to the pulley and the acceleration of the pulley itself. Okay, so the real acceleration of m1 is the acceleration of mass m1 with respect to the pulley and the acceleration of the pulley. Okay, if you look at the acceleration for mass m2, it is the acceleration of the pulley downwards, and from that we subtract the acceleration, the relative acceleration of mass m2, that's upwards. Okay, so that's what we do. So the interesting thing to do that is that using this kind of formalism allows us to better understand the problem and not worry about setting up kinematic equations that express the relationship between the real accelerations m1, m2 and m3. Okay, so it helps us get around that problem. So if you look at these two equations, right, so we just add them up and the tensions cancel out. So m1g plus m2g equals m1 plus m2 times a, and we we divide by m1 plus m2 to get a equals m1 minus m2 g times m1 plus m2. Okay, and if you look at the tension here, we take this and substitute that into this expression. So tension is nothing but m1g minus m1a, right? So and we plug that in here, and this is what we get for tension. Okay, now the tension T1 equals 2 times T, so we get 4 m1 m2 divided by m1 plus m2 times g. So now, knowing that, knowing the value of T1, we can plug this in here, right? And we divide both sides by m3, so to get a3, so we divide both sides by m3, so we get a3 equals this value, 4m1 m2 divided by m1 plus m2 times m3 times g. So if you want to find the true acceleration, okay, for m1 is nothing but a plus a3. Okay, a is something that we found already, and a3 is something where you just found, so we just add them up, right? We just add them up and we take g divided by m1 plus m2 as a common factor, and so that's what is left in the brackets. And so the true acceleration of m1 is nothing but g divided by 1 plus m2 times m3 m1 minus m3 m2 plus 4 m1 m2 divided by m3. So that's a very important expression for the acceleration of mass m1. Okay, so I hope you've understood, how the choice of the reference frame can make it easier for us to solve this problem, or at least these kinds of problems. If you've liked this video, please press the like button and please subscribe so that you can get updates to further videos in the future. Thank you.